Hello. In the lecture, we talked about models that had both a factor covariate and a numeric covariate. And then we looked at additive and interaction models and talked about what the difference between those two are. So in this video, we're going to look at applying those concepts to a real data set. And we're going to go back to this Berkeley Guidance Study Data. So to load in the data set, we'll use the data function. And we'll specify which data set we want and which package it comes in, which is ALR4. And then we're just going to take a peek at the data. So the first thing I'm going to define is the number of rows, n. So there are 136 rows in the data set. And then we're going to use the head function to peek at the first 6 rows of the data. So our response variable, we're going to use height at age 18. And the two most important variables we're going to look at for this lecture are height at age 9 and sex. So height at age 9 obviously is the height in centimeters measured at age 9 during this longitudinal study. And then sex is either coded as 0 or 1. So the first thing we have to do is to figure out what that coding means. So in the, so I'm in the console, so I'm going to press Control-1 to go back to my R script. And in the, we're going to look in the documentation for this data set. So the package is ALR4. So to look at the documentation for the BGS all data set within package ALR4, we do ALR4 : BGS all. And I hit Control-Enter to run that. And this pops up the documentation. So the first column it outlines is the sex column. And so this tells us that 0 is males and 1 is females. And then it has every other variable here. Okay, so that's good to know. We wouldn't want to miscode that. So let's go back over here. So what we're going to do next is create a variable that allows us to put colors on plots according to the sex. So before we do that, we're gonna use an indexing technique, and I want to kind of review for you how this works. So to demonstrate this, R has a built-in object called letters. So if I hit Control-Enter, it will print that out. And these are just the letters A through Z in lowercase. So to index this vector, I can say, for example, letters of 1 is A, of course, and and I can put in a vector of indices here. So 1, 2, 3. So this will give you A, B, C. And then I can put in whatever I want here for the vector. So if I do 3, 15, 18, 14, 5, 12, 12, that spells Cornell. And in particular, I can put in the same index twice. So there's 2 L's at the end of Cornell. So I put 12 and 12 at the end to add those two. So even though letters itself is a vector of length 26, you can index it kind of in any way you want. So for example, actually let's just go crazy with this. So if I repeated the number 26 100 times, this is going to be 100 Z's because Z is the 26th letter. Okay, so that's how that works. And so we're going to use this concept to create a color vector. So let's look at this sex variable. So this is coded as 0 and 1. And I'm going to create another vector called toColors. That's just the words or strings black and magenta. So here toColors is going to play the same role that letters played in this example. And then to index it, we're just going to look at BGS all $sex plus 1. This is going to be either 1 or 2. So the 1s now correspond to males and the 2s are females. And then we're going to index toColors with this vector. So wherever there's a 1, you're going to get a black, and wherever there's a 2, you're going to get a magenta because the first index of 2 colors is black and the second index is magenta. So if I define callvec to be that, now this is either black or magenta, and the black strings correspond to the males and the magenta strings correspond to the females. All right, so now we're going to use this to create a plot. So if I call the plot function with BGSAlt height 9 on the horizontal and height 18 on the vertical, and then I color this with callvec, now I'm going to get 2 different colors for the points, and the magenta ones are the girls and the black ones are the boys. Okay. Now, for someone looking at this plot, it's not going to be clear which is which. They might be able to figure it out based on their knowledge of biology, but let's make this clear. So we're going to use the legend function. So let's look at the documentation for the legend function, because this one's a bit complicated. So the way this is called is you can specify coordinates in the sort of the coordinate system of the plot with X and Y. So this will tell you where to put the legend. But if you look at this XY argument, you say X and Y coordinates to be used to position the legend. They can also be specified by keyword or in any way which is accepted by XY.coords. So what that means is there's a few number of keywords that make it easy to put the legend in specified places. So in particular, there's a keyword bottom right, which will put the legend in the bottom right corner. There's also top right, top left, and bottom left. So we're going to specify the legend position with bottom right. And then the legend function has a legend argument, which tells us which words are going to go in the legend. So we're going to put girls and boys. And then we're going to put plotting symbols next to these 2 words. And I'm going to use circles, which is PCH equals 1. So PCH controls which type of plotting symbol you use. And then I'm going to use the color of the plotting symbol, namely magenta and black, to specify which color is girls and which color is boys. So if we run this, I just hit Control Enter. Now we have this legend in the bottom right, and shows you that the magenta one are girls and the black ones are boys. All right, so I'm going to be making a bunch of plots, and I don't want to have to specify this, 6-line piece of code in order to add a legend, because the legend is going to be exactly the same on each plot. So I'm going to write a function that does it for me. So I think this is the first custom function we've done. But basically how writing a function works, and you'll do a lab on this actually, is we define the name of the function. So the name of the function is going to be called add legend. And then I assign something to add legend with this function. So there's a function called function, which is used to define functions. And the way this works is you specify the parentheses here. If you want to add any arguments to the function, you can add them here. But this function is going to be the same legend every time. So we're not going to have any arguments, so we leave that empty. And then what goes inside of these curly brackets are the code that you want to get run every time you call the function. So the code I want to get run is just precisely this call to the legend function. And so I've just copied this thing, these lines, into what's called the body of the function, which is everything that's in between the curly brackets. And I've just made the code a little bit more compact. So if I run this, now I have a function called add legend. And if I create a new plot, so once I create a new plot, it hasn't added the legend yet. And then I can just call this add legend function, and it will put that legend there. Okay, so that's your first custom function. The idea behind this is twofold. One is that it makes the code shorter. So you don't want to have to repeat these 6 lines of code every time. So basically you have 4 lines of code here, plus just 1 additional line each time you create the plot. The other thing is that if you're making a lot of plots, like say for a paper, and you want to have consistent legends, then you want to just define this one time. So for example, if you had 10 plots in the supplement to your paper with the same legend in each one, if you wanted to change that legend and you were writing the code this way, where you did it the same each time, you would have to change this in 10 places in your code. Whereas if you write a function and you want to change the legend, you can just change it once. So for example, if I look at this legend, I actually don't quite like this. Actually, there's a mistake. What did I do wrong? Oh yeah, I typed boys, girls. Oh, perfect. I did this on purpose. I made a mistake. So the boys are magenta here and the girls are black. So what I'm going to do is I'm going to switch the colors. So I'm going to say this is black, this is magenta, and I'll rerun the function. I'll rerun the function to define it. Okay, and now this is better. And if you'll notice, this is actually different from this one because it has the boys on the bottom and the girls on the top, whereas this has the boys on the top and the girls on the bottom. It's a subtle difference, but I kind of like this one better because it doesn't trick your brain, because the boy points are generally, not always, but generally above the girl points, and so it makes sense to define the legend in the same way. Okay, now moving on, let's fit some models. So the first model we're going to fit is just a model that has height at age 18 as the response, and then a single numeric covariate, height at age 9. All right, so that's that model. Let me print out the summary. So this is just a sort of a simple linear regression. And let's just look at a few things. So the intercept is 32 centimeters. That's not too meaningful to us because there's no people in our data set that are height 0 at age 9. The height at age 9 slope is 1.03. So the interpretation there is for every increase of 1 centimeter at age 9, we expect an increase of 1.035 centimeters at age 18. So how good is this model? So we can look at r squared, which is 0.41, so it's not great. So there's a lot of variation in the response that's not explained by height at age 9. Residual standard error is 6.8 centimeters. So what that means is we can predict age 18 height with this model within about 7 centimeters either way. Okay. Now, of course, if you look at the plot, let me just pull the plot up again. There's obviously a lot of variation that can be explained by sex. So nearly all of the black points are above the magenta points here. So what we're going to do is we're going to create a variable that treats sex as a factor. So I'm going to call that sexfac. And the way I'm going to define this is I'm just going to initialize it with NAs. So this is all NAs. And then I'm going to look at all of the indices for which the sex variable is 0, and I'm going to assign male. So just to remind you how this works, this is going to be a true-false vector. This BGS all $sex equals 0. And it's going to be true for all the indices that correspond to the males. Remember, those were the first ones. And I'm going to assign those to be the string male. And then I'm going to do the same thing for female, but I'm going to do all the indices for which sex is 1. I'm going to assign female. And then I get this variable here. So this is not a factor, actually. This is a character vector. So you can do, so for example, if I do class sexfac at this point, it's a character. To convert it to a factor, I use the function as.factor. And now if I print it out, it's going to indicate to us that this is a factor because it prints the levels out. If we want to be 100% sure, we can check the class, and now it's a factor. And then to keep things kind of neat, I'm going to add this sexfac as a column in BGS all. So if I do that, so BGS all $sexfac equals sexfac, and then I do head, now I have an additional column over here, which is the sex factor. All right, so now we can add it to the model. So the first model I'm going to do is I'm going to do height at age 18 as the response, and then I'm just going to do a regular old factor model with sexfac. Now, by the way, I can accomplish the same thing with this 0, 1 variable sex. If I just convert it to a factor, I get that. And these are exactly the same model. Now the parameterization is going to be different. So let me print out the first one. So this is the one with sexfac. So this is a one-factor model where the factor has 2 levels. So there are 2 model degrees of freedom. The constraint that are imposed is it set the coefficient corresponding to female to 0. The reason for that is because it coded female as the base level because it comes first alphabetically. So the way I interpret this is that the expected height at age 18 for females is 166.5 centimeters. And then the expected height for males at age 18 is intercept plus this coefficient here. So it's 166.5 plus 12.4, which is like I'm going to do math in my head here, 178, or just under 179 actually. Okay, so this model tells us that males are on average taller than females, which is what we expect. Now let's look at the other one, summary M2A. So before we print that out, what are some things we're going to look at? So residual standard error is 6.293. Multiple R squared is 0.4974. So let's print this one out. You see that you get exactly the same residual standard error and exactly the same multiple R squared. So that should be your clue that this is actually the same model. But here the parameterization is different. So what happened here is since this, let me print this out for you, BGS all $sex. Because this is coded as 0 for males, 1 for females. When R converts it to a factor, it looks at the string 0 and the string 1 and decides that 0 should be alphabetized before 1, and it sets the base level to be 0, which corresponds to males. Now that's the opposite of what it did when it had male and female as the 2 strings. Female came before male alphabetically. But here 0, which is male, comes before female alphabetically. Before 1 alphabetically. So the intercept here corresponds to the expected height for males at age 18, which is indeed 179. And then the expected height for females is going to be just that minus that same coefficient, 12.43. Okay, so this is the same model. It just had made a different choice for the baseline level. And so therefore this the interpretation of the coefficients is different. Okay, so that's M1, remember, was a model with just height at age 9. M2 is a model with just the sex as a factor. And now we're going to put these together. So we're going to define an additive factor-numeric model. So again, the way you do this in R is we have the same response that goes to the left of the tilde. And then to define an additive model in two variables, you just put in the two variables and you put a plus between them. So when you see plus, think add, and then think additive. So plus means an additive model. So it's that easy to fit the model. And then we'll do the summary. Okay, now let's spend some time figuring out what these parameters mean. So we have an intercept. Actually, before that, we have this sex fact male. So remember that it coded female as a baseline level. And so since you should be reminded of that when you look at the coefficients and you see only the male and not the female. So that should be a clue that it coded female as 0 as the baseline. So what this model means is we have a model that is linear as a function of height at age 9. But there's two different lines, one for the first level of the factor, one for the second level of the factor. So one for female, one for male. And these two lines have the same slope, but they have different intercepts. So let's try to figure out what is the intercept for females and what is the intercept for males. So the intercept for females is going to be simply, remember that this is B0 plus B1, and it coded B1 as 0. That's the constraint it made. And so this thing is B0. This is the intercept for females. So the intercept for females is 36.8. This number is not really all that meaningful on its own because, again, this is the expected height for females when height at age 9 is 0. So this is kind of a big extrapolation from where our data are. But the difference in intercepts will be meaningful here. So the difference in intercepts is going to be this coefficient, 11.69. So what this means is that the intercept for males is 36.8 plus 11.7. So the two lines are going to be parallel, but the male line is going to be higher than the female line. If you think back to our plot, that's exactly what we expect to get. And then the slope of these two lines is this coefficient, 0.96. All right, so let's compare these three models. So if we look at M1, we'll compare it on residual, standard error, and multiple R squared. So the model which is height at age 9 had a residual standard error of 6.8, R squared of 0.41. M2 had the sex factor. Residual standard error is 6.3, which is smaller, and has a higher R squared. And then M3 has both. This has a much smaller residual standard error, 3.4. So this tells us that this model is a lot better than the other two. And the multiple R squared is much higher as well, 0.85. So you can explain 85% of the variation in the response with just these two variables, height at age 9 and sex. Okay, now let's be formal about comparing these models. And so we're going to do an F-test. So if you think about this, there's kind of two interesting F-tests. So the first one would be, so they're both going to have the additive model as the full model. And the two F-tests are going to correspond to two different reduced models. So if we want to compare the model that just has height at age 9 as the reduced model, we'll do ANOVA M1, M3. And this is nice. It gives you a little table. It says the reduced model is this, the full model is this, and then it prints out residual sum of squares and an F statistic, and this is highly significant. So just as we saw by looking at the residual standard error, it went down a lot when we added both variables in the model. And so this is not surprising. Now the other comparison is this one. This is comparing the same full model, but the reduced model is just the one factor model with sex. This again is going to be highly significant because the residual standard error for this model was much smaller. So we get a F statistic of 317, which is huge. Okay, now the ANOVA function is not that smart. So it will allow you to do things that don't make sense. So for example, if you were to compare the model with just height at age 9 to the model with just sex in it. You could do that with the ANOVA function, but this does not make sense as an f-test because these two models are not nested. So if you look at these two, you can't, if you treat this one as a full model, you can't get this reduced model by sort of eliminating things from the full model, and vice versa as well. So R doesn't print an error here. It does give you a little clue because the residual degrees of freedom are the same. But there'll be cases where you'll want to compare things that don't make sense, where the residual degrees of freedom are different, and it will print out an f-test as if nothing has gone wrong. So be careful with this ANOVA. You really have to check yourself that the models are actually nested. All right, now let's visualize this model fit. So I'm going to just plot the data again. So that's the plot. Now, if I want to get what I want to do, where are we going here? We want to put lines on the plot. And so what I have to do is extract these model coefficients. So remember, M3 was our additive model. And there's a field inside of M3 called coefficients. And this tells us the intercept, the slope, and then the difference in intercepts. So what I want to do is I want to put two lines on the plot, one corresponding to females and one corresponding to males. So there's a function in R for adding lines to plots. It's called AB line or AB line. And it takes several arguments. The first argument is an intercept, and the second argument is a slope. And then you can specify all sorts of parameters like the line type and the line width and the color. So I'm just going to specify the color here. So to do the female line, the intercept is going to be the first coefficient. So that's this number here. The slope is the second coefficient. So I'm going to do M3 coefficients 1, comma M3 coefficients 2. And then I'm going to make this a magenta line to correspond to the colors we've chosen. So that's that. Now to add the male line, this is slightly more complicated. Remember that the intercept is going to be intercept plus sex fact male. So for the intercept argument, I'm going to have to do M3 coefficients 1 plus M3 coefficients 3. And then the slope is the same. And then I'm going to make this one black. So if I run that, I get that line. So to visualize this, this is what it looks like. These two lines are parallel because it's an additive model, which means that the difference between the line here, the two lines here, is the same as the difference between the two lines here. And then I'll add my legend. So this is where our function is going to come in handy. Okay, now the most complicated model we talked about is the interaction model. So before we fit this, let's just remind ourselves what the interaction model does. It has a line for girls and a line for boys, and there are no restrictions on how those two lines have to be related, meaning that the girl line has its own intercept and its own slope, and the boy line has its own intercept and its own slope. Now to fit the interaction model in R, it's going to be very similar to the additive model, but because it's not additive, we're not going to use a plus, we're going to use the star. So star will tell R to fit an interaction model. So M4 does that. It's done. It's very fast. And let's look at the summary. And I'm going to go ahead and print out the ANOVA as well. All right, so here's the summary. So how do we interpret this? So remember, with the factor-numeric interaction model, there are too many parameters, which means we need two constraints. So the constraint it picks is that B1, remember the intercept for the baseline level is B0 plus B1, and it sets B1 equal to 0. And the slope for the baseline level is C0 plus C1, and R will by default set C1 equal to 0. So that means that B0 is interpreted as the intercept for the baseline level, which is female. So 48 is the baseline level for female. And this HT9 is C0. That is the slope for the baseline level, which is female. So these two numbers tell you everything you need to know about the line for girls. The intercept is 48 and the slope is 0.87. Now the intercept for males is going to be this number plus B2, which is this number, so 48 minus 13. And the slope for males is going to be 0.87 plus 0.18. Okay. You can see that this model is a little bit better, has a little bit smaller residual degrees of freedom, but not a lot smaller. So this isn't going to be a wildly better model. And the multiple R squared is about the same. If we look at the F test to compare these two. Now, if we look at these two models, this one is nested because basically in the interaction model, you're adding terms to the additive model. So this is a fair comparison for the F test. The F statistic is 2.96, so this isn't that big. And the p-value is 0.08. So what this means is we have not very strong evidence that the slopes for females is different than the slope for males. All right, now there's something a little bit puzzling that I skipped over. If you remember back to the additive model, the intercept for males was higher than the intercept for females. Do we have that printed out somewhere close? Yeah, here it is. So the intercept for males was 11.7 higher than the intercept for females. Now, if you look carefully at these coefficients, you see that the intercept for males is actually lower than the intercept for females. So that should maybe raise a red flag. Like, did I actually fit the model that I thought I was fitting? Because really the line for the males should be above the line for females. So what I want you to do is pause the video and take a second and think about whether this makes sense or not. And I'm going to give you a hint that yes, it does make sense, and we have not made a mistake. But I want you to think about why it does make sense. So pause the video and think about that for a second. Okay, we're back. Now, without explaining it in math, I'm just going to plot the lines to show you why it does make sense. So back over here, Control 1. That's the plot of the data. Now, I'm going to add the line for females, and I'm going to add the line for males. So the intercept for females is just the intercept, so that's the first coefficient. The slope is the HT9, which is the... Actually, let me print this out for you. M4 dollar coefficients. Remember, the intercept for females is this one. The slope for females is this one. The intercept for males is going to be this plus the third one. And the slope for males is going to be this plus the fourth one. So here is the female line. That's the intercept. That's the slope. I put some extra parameters in there. LWD equals 1. That's the default. So I'm going to remove that. That should do the same thing. For the males, I have to add two things together to get the intercept and two things together to get the slope. I'm going to get rid of this. So that's the male line. And there's my legend. Okay. Now, if you look at the lines, there's really nothing weird about them. The black line goes through the black points. The magenta line goes through the magenta points. And the black line is always higher than the magenta line, which is what we expect. However, the intercept of the black line is actually 13 lower than the intercept for the magenta line. The reason for that is that this line has a higher slope than this line. And the intercept is going to be like way, 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 way over here off to the left, off the screen. And so even though the black line is higher everywhere within the range of the data, if you were to extrapolate these two lines, the black line actually intersects the magenta line before they get to 0, and the black line ends up being lower than the magenta line at 0. So that's the explanation for why this number is negative, that the male intercept is lower than the female intercept. Another thing to notice about this is that the standard error for this difference in intercept is actually pretty large. It's about the same magnitude as the difference itself. So why would that be? The reason is that since this is like sort of looking at what's the difference between the two lines at 0, and 0 is like a huge extrapolation outside of the data. So the model correctly tells you that you do not have much information about the difference between the two lines at height age 9 equals 0. So it correctly tells you that there's really no data over there, and so you have no information about what that difference is. Now in the additive model, let's go back to the additive model. Here, this is the difference in intercepts. It had a much smaller standard error, and that's because it's using the fact that you're assuming that the lines have the same difference everywhere. So if you can use the data to determine that the line is 11.7 higher, the line for male is 11.7 higher than the line for female in the middle of the data, your assumptions allow you to extrapolate that down to height at age 9 equals 0 and say that the line at 0 is 11.7 higher. And that's purely because you've assumed that the lines are parallel everywhere. Whereas here in this interaction model, you don't assume it. And this is interpreted as the difference between the lines at 0. And you're correctly saying that you actually don't know what that is. And that's because you haven't assumed that the difference between the lines is the same everywhere. Okay, so if you do the t-test, you get something that's not significant. So basically it says, I don't have good evidence that these two lines are different at 0. All right, now the last thing I want to look at is a transformation of the data. So one thing that can often happen is that if you fit a model to the raw data, you'll see an interaction. But if you take the log of the response and the predictor, then the interactions can go away. So without getting too deep into this, the reason why that can sometimes happen is because in an interaction model, you have two terms multiplying each other. So you'll have the dummy variable for sex multiplying the height at age 9 number. And the property of logs, let me just type this out so you can see it. Really, the interesting property of logs is that the log of A times B equals log of A plus log of B. So this is kind of the defining property of what the logarithm does. So what it does is it takes this multiplication of A times B and it splits it into a sum. So you can think of this as like it's taking an interaction and it's converting it to additive. So this is why often when you take a log, if the truth is multiplicative on the original scale, taking a log can break that multiplicative relationship and turn it into an additive relationship. So what we're going to do is we're going to plot the log. So on the horizontal axis is the logarithm of height at age 9, and the vertical axis is logarithm of height at age 18. And we're going to fit M5 is not going to be too interesting to us. M6 is the additive model in the logs. M7 is the interaction model in the logs. We can print these out. Let me take a look. Let's look at the interaction model. So this one tells us the difference between the two slopes on the log scale. And so you get 0.09, and the standard error is 0.08. So here's another case where the standard error of the estimate is roughly the same magnitude, and therefore you're not going to get a rejection. So we'll do the F-test, but what you're going to find is that we don't have enough evidence to conclude that the relationship is not additive on the log scale, which is sort of what I was trying to argue with this log A times B equals log A plus log B. So here M6 and M7 is additive in interaction. Here's the F statistic 1.3, which is pretty small, and here's the p-value, which is not significant. So I'm not going to go through all the code, but I'm extracting the lines for the interaction model, and I'm plotting them and adding the legend. So this is the interaction model for the log transform data. And what you want to notice here is that these two lines are not exactly parallel, but they're nearly parallel. And so we're concluding that we don't have enough evidence to say that the lines are not parallel. Okay, so that's an introduction to models with factor and numeric covariates. The important thing to remember is that in these models, each level of the factor gets its own line. And in the additive model, the intercepts of those lines are allowed to vary among the levels of the factor, but the slopes are required to be the same. In the interaction model, both the intercepts and the slopes are allowed to vary among the levels of the factor. So that's the key distinction. And if you think back to the math, let me plot this one out. Here's the interaction model on the original data. What an interaction model means is that, let's look at height age 9 equals 145. The effect of changing from female to male is this amount, the difference between the two lines. Whereas at height age 9 equals 125, the effect of changing from female to male is this amount, which is different from this amount. So the effect of sex depends on height at age 9 in the interaction model. And that's the defining characteristic of what an interaction really means.